because here, here the blue one, 3 protons feed 1 carbon. Okay, here two green protons feed 1 carbon. So obviously each proton needs to give up more electron density. So the green protons offer lower electron density than the blue protons. Therefore, chemical shift value of green protons is higher. And along the same line, see, in this particular proton, look at it, you have a single proton feeds the electronic need of 1 carbon. 1 proton feed electronic needs of single carbon. So this proton has even lower electron density than CH2 protons. So the chemical shift value is even higher. So this is 1.6, and the CH2s usually around 1.2. It's not. I'm not asking you to memorize the value. Just say if I put structurally similar CH3, CH2, and the CH, put them for you to compare, you should be able to know the CH. Okay, has a higher chemical shift value than the CH2, and the CH2 should have a higher chemical shift value than CH3. Okay, when everything else they are comparable. Okay, and the other thing is about the like here the red protons. Okay, they are methyl protons, but its chemical shift value is much higher than typical methyl protons. Typical methyl protons around 0.9 ppm, and here it's significantly higher. Why? Because those 3 methyl protons, they are bonded to sp2 hybridized carbon. And as I have argued earlier this semester at the beginning, and quite a few times last semester, if you were with me, sp2 hybridized carbon is somewhat more electronegative than sp3 hybridized carbon. Somewhat. Okay. Why is somewhat more electronegative? You can, watch the recordings. I think maybe even second class or something like that. The third class. Okay. I did argue there. Okay. So sp2 hybridized carbon is more electronegative than sp3 hybridized carbon. So this sp2 hybridized carbon will exercise a little bit the electron withdrawing power by inductive effect. So still some electron density away from this carbon makes this proton electron density is somewhat lower than the electron density on those protons. So the chemical shift value, yeah, it's noticeably higher. Okay, not dramatically, but noticeably higher. And same argument here. Those 2 red protons, okay, they are benzylic protons. Okay, so they are CH2s. They're bound to be a bit higher. So you expect if without considering the right side influence, you consider, oh, this means supposed to be 1.2, 1.3. Okay, but this is a bit higher than that because of this phenyl group. Okay, consists of 6 sp2 hybridized carbons. So sp2 hybridized carbons, they are bit more electronegative than sp3 hybridized carbon. So this ring, okay, if we consider inductive effect, is a bit somewhat electron withdrawing. So it reduces electron density on those 2 red protons. So makes the chemical shift value a bit higher. Okay. So the benzylic protons chemical shift value generally a bit higher than allylic protons, because allylic protons you only have this this carbon only connect to one sp2 hybridized carbon. Next one is just another sp2 hybridized carbon. That's it. But in case of benzylic one, this is sp2 hybridized. This also sp2 hybridized. This also is sp2 hybridized. So it's a bit higher chemical shift value. So far everything is go by the the electron density. So far every chemical shift value systematic variation can be explained by electron density variation. But the chemical shift value you see on this slide cannot be explained by the electron activity, electron density argument alone. and need a bit more explanations. Okay, look at here. The protons connect to the double bond, carbon-carbon double bond. We call the vinyl protons. Those protons chemical shift value is unusually high, around 5 ppm. And what happens is similarly, if you look at the protons connect to the benzene ring, it's extremely high, 7.3 ppm. Okay, so this cannot be explained by the the electron density on the proton alone. Okay, so the how do we explain that? We need to consider the field effect of the the what called pi electrons. Okay, so the as we as you I hope you all understand. Okay, a double bond has two components. One sigma bond, okay, plus one pi bond, okay. And the pi bond is formed by overlap, side-to-side overlap. This, assume this is one half of the p orbital, this is another half of p orbital. This is the pi bond, okay. The side-to-side overlap, and the side-to-side overlap of the pi bond is significantly weaker than the sigma bond. So this leads to important, the property of pi electrons compared to sigma electrons. In addition to those pi electrons are much more reactive, pi electrons also can circulate to a large extent than sigma electrons because they are weakly held compared to sigma electrons, so they can circulate to a higher extent than the sigma electrons. What does that mean? That means the circulation of pi electrons will generate stronger magnetic field than the circulation of sigma electrons. Like, let's say, using this one as example, using the those pi electrons, okay, in the double bond, pi electrons, we are circulating. Let's say, it's probably easier using this one as example, okay. So assume this tendency, this sheet, this pi bond is going this way, okay. The magnetic field is going up as usual, as I said in the class, okay. So that pi electron will be circulating here, okay. Those are pi circulating here, and the circulation of electrons create a field against external field because this is again this one is a diamagnetic. Okay? So circulation of electrons create a magnetic field against the external field, so point down. Okay? But this point down only happens in the middle of the, because this is, assume this is a pi bond, right? This is pi bond. So the circulation of the electrons generate the field against the external field in the middle of the circulation. So here, this is a pi bond. Circulation is here. The generated field in the middle is against the field, the external field going up. The circular electron in the center of circulation create field against it, okay? Point down, okay? However, I hope all of you recall that's a property of magnetic field. The magnetic field always forms a loop, and always form a loop. So when the circulation of electrons, pi electrons, create a field against the external, this is going down, okay? Against the, the external field in the center of circulation. So this circulation go like this, okay? So this is the pi bond going here, circulation is here. In the center, create a field against the external field. But that magnetic field always forms a loop, okay? So when the center is against, okay, but this is a loop, magnetic field, a loop. But at this region, okay, the field generated by circulation of pi electrons actually is parallel to the external field. In this region, it's parallel to, okay? And happens that those vinyl protons, they are in a region where the field generated by circulation of pi electrons enhances external magnetic field. So those hydrogen atoms, they are in the called deshielding zone. Deshielding zone. So if the circulation of pi electrons enhance the field going, experienced by those protons, that means the resonance frequency will be increased. Okay? An increase of the frequency gives you higher chemical shift. Okay? This is called field effect. Sometimes also called anisotropic effect. And obviously for aromatic protons, because you have 6 pi electrons here, so the circulation generates a bigger field. Okay, so it's a deshielding effect is even stronger. It's not the electronic effect or field effect. So this is the schematic drawing. The circulation of pi electrons generate Be at the center of circulation is against it. Okay, but the magnetic field always forms a loop. So the center is against, but at those protons forms a loop. Okay, at those position of the vinyl protons, aromatic protons, the field generated by circulation of electrons actually will be enhancing the external field called the shielding zone. And in case of alkyne protons, the chemical shift value is actually remarkably shielded. Okay? So the vinyl protons, the 5 alkyne protons, only about 2. And you have to consider the alkyne proton is connect to sp hybridized carbon. As we know, sp hybridized carbon is even more electronegative than sp2, right? Hybridized carbon. So why the chemical shift value of alkyne proton is so low is basically circulation of electrons of carbon-carbon triple bond is different from carbon-carbon double bond. If this triple bond, okay, if this carbon-carbon triple bond, the circulation electrons is holy. This is carbon-carbon triple bond. The circulation electrons actually in this way, okay, in this way, because we have a cylindrical distribution in this way. So the order, the alkyne proton they are in the shielding zone. So it reduces the field, those protons experience. Now the last, the proton I want to emphasize is the aldehyde proton. Aldehyde proton here is directly bound to a carbonyl carbon. So the carbonyl group has a sigma, it becomes a double bond. So double bond has 2 components, sigma and a pi component. So this hydrogen or this proton is also in the shielding zone of the circulation of the carbonyl pi electrons. So also, as we know, carbonyl group is quite powerful. I'm not saying super powerful, but carbonyl group is quite powerful electron withdrawing group. So electron density on this proton also is pretty low. So basically this proton under the influence of inductive effect, so it has very low electron density. Also under influence of the deshielding effect of the pi electrons, so the chemical shift value actually very, very low. It's almost 10 ppm. These are among the most deshielded protons in the CH bond. Now for the most of the CH protons, their chemical shift value usually they are pretty well defined. They are, depending on local structure, usually you can find in the relatively narrow chemical shift value. So if you have a particular CH proton in a certain range, you can have a good sense of what kind of proton it might be. But OH and NH protons, they are quite different. Okay, so the chemical shift value of OH and NH protons, they can vary quite a little bit. If you look at you know this I don't really have it here. Okay, yes, you see, look at the OH protons. Okay, can vary a lot, can from 5 ppm to 0.5 ppm. Okay, and NH also can vary quite a little bit, 1 to 3 ppm. Why they can have such a larger chemical shift value variation is mainly because of the OH and AH group. You know, they actually can have a decent probability or decent tendency to form intermolecular hydrogen bonds. And as you should recall from general chemistry too, hydrogen bonds, they are kind of strongest form of intermolecular interaction. And if a molecule can engage, can participate in hydrogen bond, the environment of the group can be substantially changed. The chemical shift value also will change a lot. So basically, why OH and H proton chemical shift can vary a lot, basically because of the degree of hydrogen bonding could change a lot. So that's why it's very we very rarely using chemical shift value of a proton to identify OH or NH group, because the chemical shift value can change a lot. But for CH protons, you can using this table, okay, to help you find what kind of protons you might have. Okay? Like for instance, if you have CH bond connect to oxygen, then you expect the chemical shift values around 3 point something. If a CH bond connect to chlorine, also about 3 point something. But if you have a CH bond connect to carbonyl, it's around 2 point something. And if your CH bond connect to just a regular, the LQ group, it's 1 point something. It's basically based on chemical shift value. You can have a reasonable idea about what kind of protons you might have. Okay, but OH or NH bond usually is what's left over is OH and NH. But I will tell you another way help you to identify OH and NH bond. Well, we'll discuss when we get there. Now, so one of the important, the most important goal of learning NMR spectroscopy is basically if you give an NMR spectrum, you need to figure out what your compound might be. If you cannot directly tell what it is, at least narrow it down to a few possible candidates. Okay? So basically we need to learn how to interpret the proton NMR spectra. You need to decode proton NMR, the spectrum. So the proton NMR spectrum, tell us, three types of information other than chemical shift value. Chemical shift value is always important because chemical shift value tell us the local environment, the possible local environment of the the signal of interest. And I know at this point it's hard for you to have a sense of it. After we're going through multiple examples, you will gradually have a sense. Right? If you see a proton signal in a particular chemical shift value, you will have gradually develop some sense what this what this signal may come from what product you make. Okay, we'll give some examples. Okay. In addition to the chemical shift value, you also will see like how many signals you have. Okay, so how many signals, basically how many peaks you have, tell you how many distinct type of protons you have in the sample. And also equally important, the area on each signal tells you how many protons that signal corresponds to. And then the third one, the called splitting of signal, tell you the number and the types of protons, the near those protons that give the signal. Okay. Oh, we will these two informations are universally applicable to every NMR spectrum you will be seeing. Okay, the splitting, will be more complicated, but in those relatively simple cases, the splitting of the signal also are very important. Okay, so I would, basically, if you want to extract the information, go through the using this one, okay, this one, those two information, these two type of information should be used first. Okay, then before the splitting, also consider the chemical shift value. Lastly, consider splitting. Okay? So this, again, we're gonna go through a number of examples. Okay, we will see. Okay, first, let's talk about the signal integration. Means the integration of a signal is area under the peak. So the quite often, in the NMR in the NMR spectrum, in addition to the say chemical shift value, absorbance, the height is absorbance. You also see this is S-shaped curve. These are the called integration. Okay, so basically you are seeing, okay, before we getting this blue peak, is integration this much, and at blue peak you see suddenly increase, okay, of the integration value. And then after one increase slowly again, and at the red peak, suddenly increase again. So the integration value of this two peak is found by this way. Okay, so the usually what you do is let me. You see the if we look at this integration curve, this part is generally linear increase. Okay, you draw the extrapolation of linear part. Okay, and then here again you draw the linear extrapolation of linear part. Okay, then you measure the difference of here. Okay, this represents area. Okay, same thing, you draw the extrapolation line of the this part, you cross with the peak, and you measure the height here. Okay, so like here, if you using a ruler to measure it, okay, so you may find this is let's say this is maybe 2.2 centimeter. Okay, this one will be 3.3 centimeter. So what you know, the ratio, okay, the ratio between these two integration values. Okay, so the length of this height, okay, basically the length you measure here is directly equal to the area under this peak. So what you measure here is equal to the area under this peak. So what do you measure this height? Okay, is equal to the area of this blue peak. And if we measure the height on this S curve, this area of this red peak. So the only thing you know is the area ratio between blue and the red peak is 2/3. Okay. That's what you get from the 2/3. Okay. So what does that mean? Means the because in a proton and a mass, every proton can give you certain absorption. Okay. So if you there's a more type, there's more protons of a particular type, then that kind of proton will absorb more signals. Okay? So like we have two blue protons, okay, and the three red protons. So the area, okay, that the area of the peak, okay, is the result of blue protons absorbing electromagnetic radiation will be a little smaller than the area of the peak is the result of red proton absorbing the light, because you have three red protons and only two blue protons. So the area on each peak, okay, is directly proportional to the number of the protons that are responsible of the corresponding peak. Okay, so the in homework you need to do this. Basically, you have to using your ruler to measure the height on the S curve, like I did here. Okay, but in exam I will directly tell you what is area of each peak. So save you some time. So I will tell you, okay, this peak means is what is area under this peak means this is like here I will just tell you this peak is 2, this peak is 3, blue peak is 2, the red peak is 3. That means the blue peak and the red peak, the ratio must be 2/3. Okay, but it could be you have 4 blue protons and 6 red protons. That's possible. Okay, so if the ratio is 2/3, could be like we have seen here, 2 blue protons, 3 red protons, but also it could be 4 blue protons and 6 red protons. Just the ratio is fixed. Okay, the ratio is fixed. So these numbers are relative, now, I hope you, any question about the area? So like here, what are we seeing? Just, the blue, because we only have 2 blue protons in this molecule, and we have 3 red protons in this molecule. So the blue protons give you a bit smaller peak than the red protons. And if we make blue proton area as 2, the red proton area will be 3. If we make blue proton area as 4, the red proton area is going to be 6. Okay? The ratio is proportional to the number of protons that produce a signal. Now the next thing before we move further is why the blue proton, okay, chemical shift value is noticeably higher than chemical shift value of the red protons. So the red protons, you see chemical shift value here is 3.4 ppm. Why? It's basically red protons, okay, they are under direct influence of single oxygen atom. Oxygen is fairly, very powerful electron withdrawing group by inductive effect, just next to fluorine. Okay? So that's why the CH3 is usually appear if we have a CH group next to oxygen, usually around 3 point something ppm. Okay, that's I hope you're starting. This value is very important. Later you're gonna see quite a few in the alcohols. If you have a CH group direct bound to oxygen, that CH usually 3 point something ppm. Okay, if you don't have other structure impacting its chemical shift value. Now, if you look at the blue proton, okay, on the left side, on the right side of blue proton is direct bound to oxygen. Okay, so this oxygen will steal electron density away from blue proton. Okay, But don't forget at the left side also has a CN triple bond connect to it. And the CN triple bond, if you recall what we learned in chapter 13, is also a kind of mediumly powerful electron joining group. Not a simple powerful mathematical group, but also it's reasonable powerful electron joining group. So if you look at this blue proton, it's under the direct influence of two electron with joining group, Cn and O. Okay, so no wonder its chemical shift value is substantially higher than the CH3 protons. So these are just the one bring to your attention. Now after knowing the basic the peak area matters that relate to the number of protons that give the peaks. Okay, then we're going to try to answer the question Isabella bring up. How do we know if a molecule has many protons? How do we know what kind of protons give a same signal? What kind of protons give different signals? First is look at chemical shift value. Okay, if the local environment is different, obviously chemical shift value will be different or give different peaks. Like CH2 and the CH3, obviously they're different, right? That must be different. Everyone can see that. Okay. Under the same thing here, those two protons they must be different because one is directly bound to the chlorine. Okay. The other one is a bit farther away from chlorine. So these are obvious. Okay. But what about the, let's say, the two protons connect the same carbon, whether they are the same or not. Okay, so for those more complicated situations, if you're not so sure, you always can make test molecules out of using the protons in question. Okay. Oh, okay. I hate that. I cannot see my cursor. What happens? Maybe you have to change this. Okay. So let's say if we're looking at that's using propane as example, say let's ask, okay, as I'm not sure the blue and the red whether the blue and the red protons are the same one. Okay, one way, I think for most of you probably just gut feeling they are the same. Okay, but if you're not sure, you can always do a replacement test. So what's the replacement test? Is we're gonna use a group or atom replace the two hydrogens in question one at a time. Okay, so let's say we're using a group that you don't already have in the molecule to replace the red hydrogen. Okay, so let's say we can using say fluorine. Okay, so we replace the red hydrogen using fluorine, then we get say fluorine. Okay, so that's one result of replacement. Okay, and then we can do same thing to replace the the blue hydrogen. So if you replace blue hydrogen, so are these two compounds the same? Do you think the replacement generates the same compound or different compounds? Are these compounds the same or not? They're the same. Okay? That means the blue and the red hydrogen, they are equivalent. Okay? So that's just the universally correct way of the testing. If you are not sure whether two hydrogens are equivalent or not, just using a group that you don't really already have in the molecule. It could be anything: chlorine, bromine, iodine. Usually I'm using halogen. If you don't already have a halogen, if you have a halogen, say you put an OH group. If you don't already have one, or OH group, and then the group replace the hydrogen of the hydrogens in question one by one. Then you see whether you are generating a pair of compounds that are different, they are the same one. If they are same, these two hydrogens, we say they are equivalent, chemically equivalent. They will give you exactly the same chemical shift value. They will give you the one signal. Yeah. Yeah, I will show you. Okay, I will show you. Okay, like like if you replace if you're checking one of those protons, methyl protons, if you replace with chlorine, say, obviously you replace this chlorine, this hydrogen with chlorine, you get this one. If you replace one of this hydrogen with chlorine, you get this one. Okay, so both of them are same compound, both are one chlorine proton. Okay, that means the methyl protons they're also the same. Okay, so all those 6 protons are the same, and all those 2 protons are same. So this compound, if you collect the proton and the Mars, you will only see 2 signals, okay? Because only 2 types of protons. And now without considering splitting, so what kind of spectrum you are expecting from propane? So you're gonna see 2 signals, okay? So basically one should be around 1.9 ppm. This one should be around 1.2 ppm chemical shift value, because the bigger one should be the metal the proton. The smaller one should be the metallic proton. And if you look at the area, this the area ratio should be the area ratio should be 3/1, okay? Because of you have 2 CH2, 6 CH3, right? 2 CH2 protons and 6 CH3 protons. So the area ratio is 1/3, okay? Because here is CH2, here you have CH3, and you have 2 of them, okay? So total the 1/3 area ratio. So that's what you're expecting from this compound up to this point. Okay? Now we're gonna show you one example. Okay, gut feeling. If I just look at your profile, the proton of interest, there must be it might be the same type, like this 2-bromopropene, the there are two vinyl protons. I believe you want that you were asking, what kind of proton might be different. Okay, like here, if you look at the two bromopropene, the blue vinyl proton and the reddish vinyl proton. Many of you may consider they are the same proton because they actually connect the same carbon, right? Correct? You might think, electronically they are probably should be same. Okay? But if you really do the replacement test, you will see that these two protons, they are different. Okay? So let's say if you are thinking about the red proton, okay, a blue proton and the red proton, okay. So what are the same? We can use a group you don't already have to replace the hydrogen, okay. So if we replace the blue proton with fluorine, okay, you get this compound, okay. And if you replace the red or pink proton here with fluorine, you get this compound. And are these two compounds the same one? They are isomers, okay? But are they same? No, because if you consider what you learned in organic 1, this is Z isomer. Because of this is high, this is high, two height of the same band, this is Z isomer, this is E isomer, okay? These are two different compounds. So these two protons are not chemically equivalent. They actually have different chemical shift values. They actually have different chemical shift values. Let me make it clear. I will test this one in next exam. Not exactly the compound, but the same type of compound. Okay. I will test your knowledge. If you have two vinyl protons connect the same carbon, you must be able to tell if the other vinyl protons also have two different substituents on it. These two vinyl protons, they are chemically distinct from each other. They are different. Okay, they will have different chemical structure. We'll be on the next test. Now, in some cases, let's say if you look at the one propanol, okay, you have the blue hydrogen and the red hydrogen. Now, if you're not so sure whether they are chemically equivalent or not, we can do the same thing. Okay, if we can using the chlorine atom, we don't have it in the molecule already, so we can use the chlorine atom to replace blue hydrogen. We get one result compound. Okay, and next one we can using chlorine to replace the red hydrogen. We get another compound, and these two compounds, they are a pair of stereoisomers. They are enantiomers. So technically, they are different compounds. Okay? They are different compounds. They are different compounds. But a pair of enantiomers, they have many properties. They are the same because they are actually mirror image of each other. So this includes their chemical shift value. So these pair of enantiomers, they have the exactly same chemical shift value. So every atom, okay? So those two protons we call enantiotopic proton or enantiotopic hydrogen. They cannot be resolved, okay? By the photon NMR instrument. Okay? So technically, these two protons, they are chemically distinct. They are different from each other, but the chemical shift value they are same. We cannot really resolve it. Okay? That's but they are they have same chemical shift value. Okay? So so far basically we learned the most important thing for you to resolve, to decode, the proton and mass spectrum is basic chemical shift value, number of protons, and the area on each case. Okay? And but if you carefully look at the proton and the mass signals of those organic compounds, especially you have a high resolution instrument, where you will see that in many cases, the NMR signal can actually can be split into multiple picklets or multiple lines because of the presence of nearby called influential proton spins. Okay, so the the product is basically influential, proton spins, just like if you have some people near you, highly influential can affect your activities, and those protons that give the NMR signal, if they have some protons at very short distance, very few chemical bonds away from it, they could influence the the line shape of the signal. So again, I will use an example to show you better. Okay? But the number of lines which a signal split into is called the signal's multiplicity. Okay, so if a signal only has a single line, we just call it singular. The multiplicity is 1. If a signal has 2 lines, we call doublet. Multiplicity is 2. A signal has triplet, meaning these 3 lines, and these 4 lines we call quartet. So in the simplest cases, okay, and that's the concept we will be using the most frequently. Okay, and the multiplicity of a signal is equal to n plus 1, and n is the number of equivalent vicinal protons. Okay, not the number of protons give the signal, is the number of protons that on the neighboring carbon, vicinal carbon, and and also it's not the protons that give you signal. For instance, if you look at the proton NMR spectra of this guy.